So here I'm going to discuss about final exam review. It's kind of summary of um, exam 1 and exam 2 and exam 3. If you think about thermodynamics, you have two approaches of studying. One is microscopic, which is statistical, and another is macroscopic, which is kind of big picture. So that's what we are focused on. And for the macroscopic, we are going to study about laws of thermodynamics. We have four laws, which is general law of thermodynamics relates to temperature measurement. First law relates to with the conservation of energy. Second law relates with the entropy and efficiency. Third law tells us that at 0 Kelvin, the entropy value is 0. This is like a reference for the entropy measurement. Regarding the energy equation, you can write energy equation or entropy equation for a closed system, open system, and isolated system. And you can write this equation in specific energy form, which is kilojoule per kg, total energy form, which is kilojoule, and then power form is kilowatt. So you should know how to write the energy equation in all these forms. Depending on what is asked in the question, we may have to use one or another. And then so that's about closed system, open system. Closed system means you have heat transfer and work transfer, and there is no mass transfer, so there is no transfer. In the open system, you have energy transfer due to heat transfer, work transfer, and then mass. Isolated system, you don't have any in the Q, no W, no mass transfer, no. So that's what isolated system is. So you should know how to write the first law of thermodynamics and second law of thermodynamics for a closed, open, and isolated system, as well as in these three forms. Okay, in specific energy form, in total energy form, and in the power form. So this is what the whole course is related with. We are focused mostly on dealing with the first law of thermodynamics and the second law of thermodynamics. In terms of application for the thermodynamics, I think we discussed about the Rankine cycle, and we also did some project work related to the Rankine cycle, where we can figure out, how different thermodynamics devices are related to produce the power in the turbine. And also we talked about refrigeration cycle, we talked about heat pump cycle, we talked about Carnot cycle, which is ideal cycle. So those are the application of thermodynamics. And the type of unit system which we'll be using are SI unit system and English unit system. In SI unit system, for the primary unit, mass is in kilogram, length is in meter, time in second, and force in Newton. And for English unit, mass is in slug or pound mass, length would be in feet, time would be in second, and force would be in pound force. So you need to see the difference between mass and pound force. You need to be a little bit careful in terms of unit conversion, and you should know how to use the unit conversion table to make necessary adjustment in terms of unit. Okay, so that's about the introduction. Now we'll try to discuss more about first law of thermodynamics for closed system, open system, and isolated system, and then we'll move on to second law of thermodynamics for the closed system, open system, and isolated system. And then we'll discuss about the general procedure, what we need to follow in solving any kind of thermodynamic problem. And again, my suggestion is always stick to the laws of thermodynamics in solving any type of problem, thermodynamic problem. Okay, so we'll start with the first law of thermodynamics for the closed system. And for closed system, again, if you see here, the first of thermodynamics is energy in minus energy out is change in energy, and this is in the total energy form. You can write in specific energy form as well as power form. So the possible way by which you have energy in and energy out is Q and work transfer, and you have no energy transfer due to mass. So this is not here, so work. So same is the case here, Q and W. And change in energy, the possible change in energy is change in kinetic energy, change in potential energy, and change in internal energy. And you don't have flow work in the closed system. And most of the cases, change in kinetic energy and potential energy are neglected in a closed system. So that is why what you get is Q Q minus W is delta U. Okay, and here the sign convention which we follow is work out is considered to be positive, and then work in is considered to be negative, which is opposite to the um, heat transfer. So that is why you have negative sign in front of this. Okay, so the work could be, so Q is always due to temperature difference. So if you want to know whether it's a heat transfer or not, if there is a transfer of energy, if it is due to temperature, it is always heat transfer, and it could be due to conduction, convection, or radiation. And any heat transfer, any energy transfer that is not due to temperature difference is work transfer. And in terms of work transfer, if it is a closed system, you could have the work transfer in the boundary, like here in the piston, this can move. And this is called boundary work. And the boundary work depends on how the process is carried out. If it is, so the boundary work is defined this way, PDV. And depending on what type of process it is, for instance, if it is isobaric, P is constant, then P can be outside, so A to the P2 minus V1. And if you add to the internal energy, it becomes change in enthalpy. If it is isochoric, there is no change in volume, so the boundary work would be 0. If it is isothermal, you can derive this is the boundary work. If it is adiabatic, you can, if it is a polytropic, this is how the polytropic is defined, this is the boundary work. So this relates to only boundary work. So that is why the energy equation becomes Q minus W boundary, and then W other, any other work. It could be 1 or 2, and then you have delta U. So this is the equation which we use um, to um, to to calculate the problem that are related to the closed system, that which is conservation of energy. So this is kind of general equation, and this is important when it is isobaric. Q minus W other is S2 minus H1 if there is the boundary work is already included here in enthalpy. Okay, so you need to be careful. And so and we should know how to get this enthalpy change or internal energy change. There are two possible routes. One is through the property table for a pure substance, and other route is through the specific heat. So those are only the two routes. And within the specific heat, there are two methods. One is constant specific heat, and other is variable specific heat. So we'll try to discuss about how you can find out delta H and delta U for any thermodynamic process. So this WB, it just relates to the boundary work. So the general equation is, when you are trying to solve the problem, this is usually the total energy equation is used, Q minus W other, any other. This is a boundary. This equals to mu2 minus u1. This u2 and u, these are the specific internal energy that you get from the property table, or you can find using the specific heat formulas. Okay, so I'll discuss more about how we can find change in delta H and delta U in the later slides. For the open system, you have energy transfer due to Q, and then W. That was in closed system as well. In addition to those, you have energy transfer due to mass as well. So when there is a mass in and out, you have this energy. So you have H, and then kinetic energy, and then potential energy. So you need to include all these energy at the inlet and outlet for the mass flow. Okay, so for the open system, so you need to consider the conservation of mass as well, because there is mass inflow and outflow, and also the conservation of energy. And for the conservation of mass, it's very similar to mass in and energy in, energy out. Instead of energy, you have mass in and mass out, and change in mass in the control volume. And if you write in, usually the power form of energy equation is used for the open systems. So this is a mass flow rate in kg per second, and then this is change in mass in the control volume. If it is a steady case, this part will go away. So summation of mass in equals to summation mass out, if you have many number of inlet and outlet. But if you just have one inlet, then m1 becomes m2. This is a very common equation in thermodynamic device where you have one inlet and outlet. And we know the mass flow rate is, the formula for mass flow rate is rho1 a1 and capital V1, which V1 is the velocity. This equals to rho2 a2 and V2. The most important thing is how the main equation simplifies to this equation based on assumptions. So whenever you solve the problem, the assumptions are very important. Sometimes some of the assumptions may be explicit, and sometimes some of the assumption may be implicit. For instance, if it says copper, then you have to assume that that's a solid, it is incompressible. So density 1 equals to density 2. If it is solid liquid, then in that case liquid and solid are considered to be incompressible, so the density would be same, and the reciprocal of density is specific volume. So v1 also v2 would be same, so you can write in terms of specific volume as well. And if it is incompressible, this will cancel out. Then this is a volumetric flow rate at the inlet would be equal to volumetric flow rate at the outlet. And if you have just one inlet and outlet, then a1 v1, this is velocity, would be equal to a2 v2. Sometimes we can find the specific volume, which is property from this equation as well. That's related to conservation of mass. For conservation of energy, again, energy in, you have through the heat transfer, you have through the work transfer, and then you need to consider the energy due to mass transfer as well. And if it is a steady case, then this part would go away. And with the sign convention, what you get is q dot minus w dot. So this is work done. We need to take all the work into consideration. And then if you have any number of inlet and outlet, then you need to consider summation of mass, and then the energy content of the mass is h plus v squared by 2 plus Gg. This is m dot, and then you need to have per outlet as well. And if you have just one inlet and outlet, you see from conservation of mass, m1 dot would be equal to m2 dot, so you just have m dot, and this is the most used energy equation for open system with one inlet outlet for a steady case. See, the assumptions are extremely important, and if you get this in power form, you can also convert to a specific form. If you divide that q dot by m dot, this should be kilojoule per kg, and so is the case for the work done as well. So this is kind of overall summary for the open system. Okay. Now we'll talk about the second law of thermodynamics that relates to the thermal efficiency and COP. So second law, one of the things that we can get from second law of thermodynamics is it tells about what is the maximum possible efficiency you can get in the thermodynamic device. Okay, and so that can be obtained from Carnot cycle, in which all the processes are reversible. So when everything is reversible, we found that QH by QL reversible at TH by TL. So you can have the efficiency in terms of temperature instead of heat transfer rate. So for heat engine, the thermal efficiency is W net out by Q in, and W net is Q in minus Q out. So what you get is this is equals to 1 minus QL or Q in by QH. So this is the thermal efficiency for the heat engine. But if it is a Carnot, you can replace this by TL by TH. So that's what you get. And for the heat pump and the refrigeration, the performance is measured using the COP. And COP is always the desired effect. In the heat pump, the desired effect is QH, and for the refrigerator, desired effect is QL divided by the required input. And this is for the actual heat pump and refrigeration. But if it is a Carnot refrigeration or reversible refrigeration, then you can replace this QH by QL by TH by TL, and this formula can be used. So this efficiency and COP for reversible heat pump and refrigeration, the value is the maximum achievable value. Uh, so that is just ideal case. So it provides us the ways to improve the efficiency of a heat engine or the COP of the refrigeration and heat pump cycle. The other thing that second law of thermodynamics does is measure of irreversibility, and the quantity that is used to measure the irreversibility is entropy, and it gives us whether a particular process is feasible or not. For the process to happen, the entropy generation has to be always greater than zero. So if entropy generation equals to zero, then the process is reversible, which is ideal case. But for all irreversible process, the entropy generation has to be always zero. Again, for second law of thermodynamics, like energy, you have entropy in minus entropy out. Now in entropy, there is entropy generation, so entropy is not conserved. So you have there is another term which is entropy. This is additional term, and this is equals to change in entropy of the system. You can write this equation for closed system and open system. Now, what are the possible way by which you have entropy in is due to heat transfer. For the closed system, this is only the way by which you have entropy in, and there is no entropy transfer due to work, and there is no mass transfer in the closed system. So the only way by which entropy can transfer in a closed system is due to heat transfer. So this is what you have, and the entropy generation is change of the system. Now, in order to find out the entropy generation, what you need to do is, if you have system and surrounding, you need to include both the system and surrounding within an isolated system. When it is isolated, there is no any heat transfer, there is no any work transfer. So when it is isolated, then since there is no heat transfer, this part would go away. So in that case, entropy generation would be change in entropy of the adiabatic system. So when you have this isolated system here in the boundary, you have both the system and surrounding within this. So entropy generation is change in entropy of the system and change in entropy of the surrounding. You need to follow proper sign convention and then find this. And always the entropy generation would be always greater than zero for irreversible process, and for reversible it is zero, and if you get negative, then it is impossible. Sometimes you may see this equation ds is dq by t, this equation being used. And if you see here, this is true only when this entropy generation is zero. So which means when the process is reversible, only then this equation can be used. Okay, so this equation can only be used when the process is reversible for a closed system. And sometimes q may be constant. If it is isothermal, t may be constant. In that case, you can write change in entropy by q by t naught. Okay. This is for the closed system. For the open system, you have entropy transfer due to q, and then you have mass in and mass out. So that is why you have, in addition to the entropy transfer due to heat, you have entropy transfer due to mass in and mass out, and this is entropy generation, and then you have change in entropy. And you can also write, this is in kilojoule per Kelvin form. You can also write kilowatt form if you have per unit time. So here m dot, and then q dot. So you are getting in kilowatt per Kelvin form. And if the process is steady, then this part would go away, and this is what we are left with. And if you have steady and also single stream, then you just have mass, single mass flow rate. When it is steady, the mass M1 dot would be equals to M2 dot, or a mass flow rate at the inlet equals to the mass flow rate at the exit. So this is why you have single mass flow rate, and this is the equation. And if it is a single stream, steady flow, single stream in adiabatic, if it's adiabatic, the heat transfer is zero. So this is what you get. So you should know how to simplify this equation based on whatever the assumptions are given, or sometime you may have to make some um, implicit assumption as well. Okay, now how do you find delta S? Because if you see in the entropy equation, the key parameter is delta S. In energy equation, the key parameter is delta H and delta U. We'll talk about this later on, but for now we'll try to see how you can find out change in entropy. Always, if possible, try to always use the property table for pure substance, whether solid, liquid, or gas, or combination of this. um, Use the property table. And there is a special case which is isentropic. If you see a word isentropic, that means S1 would be equals to S2. The other way by which you can find out entropy change is through specific heat method. And you can do for now, you need to figure out in the problem, highlight the substance, what phase are present. If it is incompressible, Cp, Cb, and C would be same. And if nothing is given, it's easier to solve the problem if it's a constant specific heat. And this is for solid and liquid. This formula can be used directly. And there is again a special case when it is isentropic, the temperature is also constant. For variable specific heat, you cannot have this outside of the integration signs. That's why you need to integrate this whole equation to get the value. And for ideal gas, if it's ideal gas, if it's nitrogen, carbon dioxide, oxygen, then um, you can use again, the first priority is to make use of constant specific heat. And this is the equation which you can have. There are two equations, it depends on what is given. So this relates to temperature change and specific volume change, and this one relates to pressure and temperature change. So depending on what is given in the problem, you need to choose the specific equation. Again, isentropic means when this equals to 0, S1 S2 equals to 0, S1 equals to S2, then a change in entropy is 0. If you equate that, this is the relation which you get between temperature and pressure, temperature and volume. And you can use, again, remember, this can only be used for ideal gas, don't use anywhere. And this is under the assumption that you have a constant specific heat. If you consider to be variable specific heat, this is the equation which you can use. These values can be obtained from the table. And if you equate, for again, there is a special case which is isentropic. When this equals to 0, then this is the relationship which you can get in solving the problem. And remember, these equation can only be used for ideal gas. Okay. And isentropy efficiency is a very important parameter in terms of figuring out how efficient the thermodynamic devices like turbine is. In the Rankine cycle, if you see that the ideal Rankine cycle, the process is reversible and adiabatic. When it is reversible and adiabatic, it becomes isentropic. So now this is just the ideal case. Now how is the actual turbine performing as compared to the isentropic case that is given by the isentropic efficiency? So for turbine, actual turbine work which you can get from first of thermodynamics, which is H1 minus S2A, and then isentropic is S2S. You should know how to calculate this S2S, S2A, and H1, and only then you will be able to calculate the isentropic efficiency. For compressor, see see the difference. The actual the lower the lower the value of um, the work you need to do in the compressor, the better it is. So the isentropic compressor work is lower than the actual work. That is why you have on the denominator the isentropic compressor work, and then actual compressor work is greater than the isentropic compressor work. That's why this is kind of opposite as compared to the turbine. Again, you should know how to get these values from the table or using specific heat method. Again, these all process ideal case are isentropic. That is why this efficiency can only be used when the process happening is isentropic. Even in the nozzle, you have isentropic process which is happening. So how does it compare to the actual case? You can use this formula to get those values. Okay. So isentropic efficiency is very important even from the exam point of view. And moving forward, if you are taking Thermo 2 courses, then you need to work on this isentropic efficiency as well, because it compares the actual case with the ideal case. Okay. If you see the first law thermodynamics and the second law thermodynamics, the most important variable are change in specific uh, internal energy, change in specific enthalpy, change in uh, entropy, and then change in even the specific volume. These are the most important property. And also pressure and temperature. If you know this, you can find out this is kind of vice versa. Even from the table, if the pressure and temperature given, you can find the property. And you should also know to go backward. If you know some property, then you should know how to find the pressure and temperature as well. Now, this is a general picture that tells us how you can find out this change in this property. Again, there are two paths for that. One is using the property table for solid, liquid, or gas, or combination of this for a pure substance. Pure substance means which is homogeneous in chemical composition. For instance, water. Water has H2O, which is homogeneous. Now, if it is a mixture of maybe oxygen and nitrogen, then it may not be homogeneous. But one of the thing is like air is considered to be pure substance, because it's kind of same chemical composition everywhere. But in general, when you have more than two gases that are present, then in that case, if the chemical composition is not same throughout, then you cannot consider as a pure substance. I think for a mixture of gases, um, I think maybe some of you will be taking course on thermo too. We will discuss about that in those chapters for mixture of gases. But here our focus in thermo 1 is just for the pure substance. And so the first priority is to get the property value from the property table. And if you are not able to get, move on to the specific heat method. And again, for any one of these properties, uh, you can use a constant specific heat method or variable specific heat method. Again, you need to look at the problem, whether it's ideal gas. If it's just a gas, and if it doesn't say anything, you can just still assume ideal gas and carry out the calculation. But if it says it's not an ideal gas, then you cannot consider. But in general, if it says oxygen, nitrogen, you can always consider to be ideal gas and carry out the calculation. If it is incompressible substance, Cp and Cv and C are constant. So this guides you through, how you can find out this property for incompressible substance, delta H, delta U, delta S, for constant specific heat. And then third priority would be using variable specific heat. If it tells you to do with this method, then only use it. Otherwise, the first priority would be using the property table, second priority would be constant specific heat method, and the third priority would be variable specific heat method. These are in the order of complexity, because it's easy to get the property value easily using the property table. The next one is, you can, if the specific heat are constant, then it's easier. But if you have to do the variable specific, it becomes complicated. Remember, you can use only this equation for ideal gas, like here, changing entropy, and this one is changing internal energy. And if you see for the gas, Cp and Cv are not same. So when you are using constant specific heat, you have Cv average, Cp average, whereas for incompressible substance, you just have C average, because Cp and Cv are same for incompressible substance if you are using constant specific heat method. If it's a variable specific heat, again, a change in entropy becomes a little bit complicated. For change in specific internal energy, Cv is a function of time, so you need to do the integration. So it becomes a little bit complicated. Now, if you see here, if you are using a specific heat method, you need to find the value of C average, Cp average, and Cv average. Those values can be obtained from the table. the A1, A2, A3. So you know, when some, if you want to know the property value, you should know where those property are. So the best way to know where the property values are is to know, you know, is to do more practice. The more practice you do, better you know in which appendix you have this property. And in regard to CP, CBR, K values, these are in A1, A2, A3, and even for A3, you have for solid, liquid, and gas. So you should know how to calculate those values. Sometime if only one temperature is given, then you can just find the CP at that particular temperature. But if you have both T1 and T2, you can find out CV average, CP average at that average temperature value. Okay. So that's about delta H, delta U, and delta S. And there is also another property if you look at the table, which is specific volume. And for a specific volume, you know, you can use the if it is ideal gas, if it is a gas, then you can use ideal gas equation. If it is a pure substance, again, you can use the property table. And sometimes the volume and mass is given, then a specific volume is volume per unit mass. If it is liquid and solid, you know, if the volume and mass are given, then you can find out this way. And sometimes the density is given, and a specific volume is the reciprocal of density. So this is one approach to find the specific volume. If it is ideal gas, you can always use this ideal gas equation, not just for this, for any ideal gas, you know, PV equals to RT, or this is specific volume, and then if you write PV, then this is volume, then it becomes MRT. And these are the gas constant. Depending on what gas you have different value of gas constant, which you can get from appendix. The other way to find the specific volume is, so if you use the conservation of mass, if it's steady and incompressible, one inlet and outlet, then you have rho 1 A1 V1 equals to rho 2 A2 V2, and then this is the reciprocal of the specific volume. So in that case, you can find the specific volume from here as well. If the velocity at exit and inlet, and then the cross section area is given, sometimes the diameter is given, and from which you can find the cross section area. So this is another way by which you can find the specific volume. Okay. This one for the ideal gas, if the density is different, and if it is for liquid, you know, the density is constant. So in that case, as we saw from the conservation of mass, the volumetric flow rate would be the same. So that's about, you know, the summary of the whole course. But the general procedure which you can follow in solving the problem is always highlight the keyword, try to see what substances are present. Is it steam? So if it is steam, then it could be saturated mixture, it could be superheated vapor, it could be subcooled. So always try to look for like what phase are present. So you need to figure out what phases are present, sometimes liquid, sometimes solid liquid. So based on that, you try to find the state property. It could be, you know, pressure, temperature, internal energy, enthalpy, density, even CP and CV. So try to figure out the property at a given pressure and temperature. So that's finding the property from the appendix, or yeah, I think mostly through the appendix, the property table. And then you need to decide which model you need to use. The model could be, you know, the energy equation for closed system. Model could be energy equation for open system, conservation of mass equation, ideal gas equation, specific heat equation. So these are available models. So choosing what phase, what substance, what phase, and then try to figure out the property. And once you know the property, you have these models, and based on the assumption, you need to simplify the model and then find out the output, the desired output. So this is the procedure which you need to follow in solving the thermodynamic problem. Substance, phase, property, and then you have type of system, you have closed system, open system, isolated system, and again which route you are going. Sometimes you have to use both conservation of mass and, you know, the conservation energy, even maybe the entropy equation as well. So even the ideal gas equation as well. So you need to choose which one best suits us. And now you have this energy equation for closed system, conservation mass closed system, and entropy equation for closed system as well as for open system. So the assumptions, the explicit assumptions that are provided in the problems are going to be very important in simplifying uh, these thermodynamic model. For instance, if it says steady, then d by dt would be 0, adiabatic, q is 0, isobaric, pressure is constant, rigid body means v1, specific volume is constant. So if it's a rigid body, then it provides the link between state 1 and 2. So b1 would be equals to b2. If it says isentropic, s1 would be equals to s2. If it is isothermal, then t1 would be equals to t2. So these are very important keywords which you need to underline, and then based on that it helps you to find the unknown property. Okay. Based on, so once you have this equation and these assumptions, explicit and implicit assumption, simplify these equations, and then find the solution. So this is the procedure which you need to follow in solving the problem. So again, this is the same thing, the key property being delta U, delta H, and delta S. Again, you have two routes, one using property table, other using specific method. And again, within that you have ideal gas route, and then you have incompressible substance, solid and liquid. Now it tells you how you can find out these delta U, delta H, and delta S for this incompressible substance and ideal gas. Again, within that you have constant specific method and then variable specific method. uh, Unless it says which method to follow, I think the priority first should be to use the pure substance. If the property values is not given for the pure substance, the second would be constant specific heat method. If it is ideal gas, you need to follow this one. If it is incompressible substance, you need to follow this one. And then the third would be variable specific method. uh, if it asks you to do the problem using variable specific method only, then use this one. Otherwise, you can stick to constant specific method if the property values are not given in the property table. And again, these CP, CB, and R values you can get from the appendix if you are using a specific method. And also, I think we talked previously how you can find out the other property, which is specific volume. And again, the value can you obtain from the property table. That's the best way. If not given, if it's an ideal gas, then you can use the ideal gas equation, and if it's liquid, you can use the equation for a specific volume if you know the volume and then the mass. And also, it is the specific volume is a reciprocal of the density. And other ways, if it's open system, you can use the conservation of mass equation as well to find out the specific volume, because the density is a reciprocal of a specific volume. So this is another way by which you can find the specific volume, provided the cross-section area and the velocity of the fluid is given. So that's kind of summary of the whole thermodynamic course. um, I think it's mostly about using the thermodynamics laws for different processes that are happening in the nature.